In today's lecture, we're going to continue our discussion of random variables, and in particular, we're going to pick up on the thread of discussing continuous random variables. So when we were introducing random variables in the first place, we discussed that there are these sort of two broad categories of random variables. You either have continuous or discrete random variables. And when we were introducing them, we sort of discussed the definitions of both of these types. But then when we started talking about how to use random variables, what they're good for, sort of all of the topics surrounding random variables, we focused entirely on discrete random variables so far. And so we'll introduce the same types of concepts around continuous random variables today, talk about a couple of named continuous distributions, and then sort of that will wrap up our discussion of probability before we move on to statistics in the next couple of lectures. And so to sort of get started here, we can recap by thinking about what is the definition of a continuous random variable. So remember that a random variable, broadly speaking, is just a numeric quantity. It's a mathematical variable, but the value of it depends on chance, right? So it's going to be a variable that somehow summarizes a particular experiment. And so with continuous random variables, what we're thinking about are random variables which can take on any value in a whole range of values. So they have an uncountable number of possible outcomes. So I will say that a continuous random variable is a random variable which takes on an uncountable number of outcomes. And so when we say uncountable, this is sort of this mathematical expression here, which simply means that we couldn't enumerate them, right? And so it's not just saying that there's sort of an infinite number of them, but it's saying that there's an infinite number of them that we couldn't count out, right? So you could count out the values 1, 2, 3, 4, 5, and so forth up to infinity. But what you couldn't do is say take all of the values between 0 and 1 and list those out, right? There's an infinite number of values there, but we also couldn't order them because any ordering you do of them, there's going to be values missing, right? And so the idea is take values in intervals, right? So for instance, all of the values between 0 and 1, or all of the values between 1 and 100, or -5 and 10, whatever, right? So sort of these intervals of possible values, okay? And so most of the concepts that we've talked about with discrete random variables are going to transfer over to the continuous case. But there's a couple of core differences that we're going to need to be mindful of. And sort of the most core difference has to do with us asking about the probability that the random variable x takes on any specific value. So what is the probability that x is equal to some value x whenever x is a continuous random variable, right? And so in the discrete case, what we saw was that this value was dependent on the probability mass function, right? So if x is discrete, then we use the PMF. And it would be really nice if we could do the similar thing in the continuous case, right? Because what we know is that the PMF sort of gives us all of the probabilistic information. But we're going to see something a little bit strange with continuous random variables, right? And so to give away the punchline, it doesn't matter what value we pick for x here. The probability that a continuous random variable takes on any specific value is always going to be equal to 0 exactly, okay? And so I'll repeat that again because I think it's a weird sort of point to make here. But if you have a continuous random variable, the probability that it has any specific value is exactly 0 for every possible value it can take on, okay? And so why might this be the case, right? And there's a couple of ways of us sort of thinking about it, but the sort of intuition is that there's just too many values to account for here, right? So if you think about a random variable that can take on any value between 0 and 1, right? We've said there's an infinite number of possibilities there. But not only are there an infinite number of possibilities there are more than the number of values that we could sort of enumerate. And so the question is, if you had that any value larger than 0, and you started adding up all of those slices which were larger than 0, right? So you have 1 in a billion, right? Well, after you've added up a billion times, you're already summed to over 1. And what we know about random variables is that the whole probability has to equal 1, right? You can't have the sum of all of the probabilities be greater than 1. And so if this value was anything greater than 0, 1 in a billion, 1 in 100 billion, right? However small you want to make this, it's always going to be the case that if you start adding these up, eventually you're going to have added up so many small pieces that you get over 1, right? Another way to think about it is that if you were to look at, say, x in the interval 0, 1, right? And then we think about something like, what's the probability that x is equal to 0.5? Well, we know that it's a continuous variable, right? So we know that it can take on any value here. And so we might think, what really is the difference between it being 0.5 or 0.501 or 0.499, right? Or 0.499998, right? Whatever. And so because there's sort of all of these values right in the vicinity of it, we don't have this with the discrete case, right? With the discrete case, we know it's going to be this value or sort of the next value in line. In the continuous case, there's sort of all of these possible values around it. And you could think about repeating your experiment multiple times, and you're probably not going to get exactly 0.5 multiple different times, right? You might get close, you might get 0.5 and then 0.501 and then 0.499, right? But you're probably not going to get exactly 0.5 a whole bunch of times. So all of that is to say, in the continuous case, the probability that x is equal to any specific value is always 0, no matter the value. So that begs sort of an obvious question. How can we characterize the behavior then, right? Because we know that the probability mass function is what's characterizing the behavior in the discrete case. So in the continuous case, how do we actually talk about the behavior of a random variable x? Okay. And so we have sort of a number of different possibilities, but the key thing that I'm going to point out is that if we were to think about intervals rather than specific points, we're going to be totally fine, right? And so, for instance, the event A, which is given by x falls in some interval from A to B, okay? We'll typically have positive probability. Right? And so what are we thinking about with this? Well, instead of me saying, what's the probability that x equals 0.5? We might ask, what is the probability that x is between 0.49 and 0.51, right? So we'd say instead of x equals 0.5, we think of x in the interval between 0.49 and 0.51. Okay. And now what we've done here is we've sort of transitioned this to an event that we can actually talk about. There's sort of actual substance there. There's actual density to this interval. And so we can start talking about the probabilities here. And so in general, we're going to think about intervals in the continuous case rather than points. And we can actually go sort of a step further than this, because it's not all intervals that we're normally thinking about, right? X in A to B, that's a perfectly reasonable interval. But we actually can simplify this down and only really think about one specific type of intervals, right? And that's specifically the intervals that start at negative infinity and go up to some value, right? So specifically, we think of x being less than or equal to some value b, right? Which we could also write as x being in the interval from -infinity up to b. Right? These two things are exactly the same interval here. And so it turns out that if all we do is think about these events in the sense of x being less than or equal to some value, this is going to let us talk about the probabilistic behavior, right? And so in the discrete case, we could think about what's the probability x is equal to some value. In the continuous case, we're going to be thinking about what's the probability that x is less than or equal to some value. And they're going to sort of be parallel with one another. Okay, and so because of that, what we want to do is we want to introduce some notation, we want to introduce some mathematical concepts to discuss this idea of x being less than or equal to some value. And we're going to do that through the cumulative distribution function, right? And so what we have here is a sort of new mathematical function, right? And what we're going to do is we're going to call this capital F. If we need to specify what random variable this is in relation to, we can write that down here like we've been doing with the PMF, right? It's not always going to be required, but we can. And it's going to take in this value x here, right? And this is simply going to give us the probability that x is less than or equal to that value x, okay? And so what we'll say about this is that this is defined for both continuous and discrete random variables. But it's a lot more useful when we're thinking about continuous random variables, right? So you could come up with this function if we have x being discrete, but as a general rule, as a continuous random variable, this is going to fully define the probabilistic behavior of the random variable itself, right? And so where we're at right now is we're trying to characterize the behavior of continuous random variables, right? We know that the probability that they take on any specific value is always 0, so we need something other than the probability mass function to characterize their behavior. What we're going to turn to is what we'll call the cumulative distribution function, or the CDF of the random variable. And what the CDF does is it tells us what's the probability that x is less than or equal to some particular value. Okay, and that's going to sort of play the role that the PMF has been playing with us up until this point. Okay, and one of the important things to note about the CDF is that with the CDF, we can actually think about any event of interest that we might have with respect to intervals, right? So we can ask ourselves, given a random variable with a cumulative distribution function f of x, what is the probability that x falls into some interval here, right? And so we can draw out sort of a number line to express what we're thinking about here, right? And so we'll have sort of these as our number line, right? It's going to go off in both directions. And if we want to know what's the probability that x is between a and b, right, a is going to be some value here, b is going to be some value here. We want to know what's the probability that x falls into this sort of area of this curve right here, right? And so the trick for us is figuring out how can we do this using just the CDF. And remember, the CDF tells us what's the probability that x is less than or equal to some threshold. And so if I take f of b, right, then f of b is going to say, what's the probability that x is less than or equal to b, which is this sort of whole area right here. Right, and so if I start with that, what you'll notice is that there's a lot of overlap with this interval, right? If we're looking at the interval between here and b, right, we're sort of overlapping it, but the issue is that we have sort of all of this extra space down below the a here, okay? And so if we think about what that extra space is, right, if we come in here and we think about f of a, then f of a is going to be this whole region down here. And so the interval that we actually care about, if we sort of look at the graphic that we have on screen here, is going to be the difference between f of b and f of a, right? And so if we take f of b minus f of a, then that's going to give us the probability that we're in the interval, right? And that's because if f of b, if we remember, is the probability that x is less than or equal to b, f of a is the probability that x is less than or equal to a. And so if we say, okay, take the probability that x is less than or equal to b minus the probability that x is less than or equal to a, and we take the difference between those two, we're left with what's the probability that it's between a and b. Okay, and so what we can say is that in general, the probability that x falls in the interval a to b is always going to be f of b minus f of a. And this will hold for the continuous random variables here. But what this little expression does for us is it lets us go from the CDF to any event of interest that we might have, right? And so sort of what this is showing us is that if you have the CDF, now we can actually calculate all of these sort of probabilities of interest. Okay. So we can sort of see this as an example coming up. And with this example, what we're thinking about is that a bus is going to arrive anytime during the next 15 minutes. And what we're saying is that it's equally likely to show up at any point during this interval. Okay, and so we're asked about what's the probability that it's going to show up in the next 5 minutes or less. Okay, and then we're asked some other questions about it here. And so there's sort of two ways to approach this question. The first way is, and if I had given you this on an actual test or exam, this is how it would have proceeded, is I could tell you what the actual CDF is, right? So I could tell you what the CDF in this situation is going to be, and we could work from there. And so what I will do is I will come in and we could say that the CDF is going to be equal to x divided by 15, right? And so if this is given, then we could approach this question here. Okay, and so why don't we do that to start, and then we can talk about how we might have done this without knowing this process, okay? So we want to know, what is the probability that it shows up in the next 5 minutes or less, right? And so what we want is, what is the probability that x is less than or equal to 5, which is by definition the CDF with 5 plugged into it, right? So based on our CDF, that's 5 over 15, which is going to be 1 in 3. Okay, so the probability that it shows up in the next 5 minutes or less is 1 out of 3. But could we have done that without knowing the CDF? And so the key point that we're going to note here is that it's going to be equally likely to show up at any point during the interval, right? So what are we saying? Well, what we really are saying here is that if we're just thinking about intervals, right? If we know what proportion of the time those intervals are going to take up, then that is going to give us sort of our probability, right? Because we know that every instant is sort of as likely as any other instant. And so then if we take a 5-minute stretch, that 5-minute stretch has to be equally likely to any other 5-minute stretch. Okay, and so sort of if we think about this here as our 0 to 15 minutes, okay, then we could put in our 5-minute mark here, our 10-minute mark here, and then we go to 15, and we'll pretend that those were drawn in such a way so as to be actually equal distance apart from one another. But what we're saying by knowing that it's equally likely is that being here, which we can call A, being here, which we can call B, or being here, which we can call C, they all have to have the same probability, right? Right? The probability of A has to equal the probability of B, which has to equal the probability of C, right? Because it's equally likely to show up anywhere. And so if we've divided this up into equal sized chunks, then it has to be equally likely to fall into any of these. But now we're in the discrete case, right? There's only 3 possible options. Either you're in A, you're in B, or you're in C. All of them are equally likely. And so then what we know is that each one of those would have to be 1 over 3. Okay, and that gives us the same result here. And so sort of 2 ways of approaching this problem. We can either discretize it and sort of think about it reasonably, and it's going to work well here only because we're sort of equally likely anywhere, or we can sort of take the CDF as given. Now, what is the probability that it shows up exactly 7 minutes from now? I will re-emphasize our point here. Anytime we're dealing with a continuous random variable, the probability that it exactly equals some value is always going to be 0, right? So with this type of question, we don't even need to think about what situation we have going on. We know x is equal, or is a continuous random variable, so the probability it equals 7 is going to be exactly 0. Okay, that's just free. It's given to us for sure. The last point here is, what's the probability that it shows up between 8 and 12 minutes from now? Okay, and so this is the question of the form, what's the probability that x is in the interval a to b, right, where a is equal to 8 and b is equal to 12. And what we know is that we can write this as the difference between the CDF at b and the CDF at a. So that's going to be f of 12 minus f of 8, right? So that's 12 over 15 minus 8 over 15, which should give us 4 out of 15. Okay, and so there's the way that we could do this sort of directly. Again, I will point out that if we thought about this sort of in our interval here, right, so we can go up to 0, up to 15, say, and perhaps you divided this up into equal size chunks, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and then we'll erase the numbers here. So then what we know is that each one of these chunks is equally likely, right? And so what's the probability that we're here? Well, that has to be 1 out of 15, or the probability that we're here, that has to be 1 out of 15 because we're in this equally likely model, right? And so then what you would have to do is count, how do you fall between 8 and 12? Well, you'd have to be after the 8, before the 12, right? So that's 1, 2, 3, 4, 5, 6, 7, 8. So somewhere between 8, 9, 10, 11, and 12, right? So something like this. And right here, you should find that that's going to be 4 out of 15 pieces summed up, right? So again, using the algebraic way is going to be generally more applicable, but it is good to sort of try to connect it to what we've been doing up till this point. Okay. Now, we can sort of take on an additional example here, and here we're just given explicitly a CDF, right? And what we want to know is what's the probability that x is larger than 8,000, right? And so we were told this expression here, what's the probability x is larger than 8,000? And the point here that I'm going to make is that all of the rules of probability are still going to hold for us. All of those secondary properties that we've been working with, all of sort of those tricks that we've been using to make computation a little bit easier for us, all of that is still going to be relevant. And so if we want to know what's the probability that x is larger than 8,000, right? One way that we could think about doing this, because we don't know how to directly solve for the probability being larger, right? But what we could say is, well, that's going to be 1 minus what is the probability that x is less than or equal to 8,000, right? And that's using our complement rule. This is sort of the trick we've been using all term long here. And now the nice part is that this is 1 minus x being less than or equal to 8,000 is simply the CDF with 8,000 plugged into it, right? And so then we can come up to the expression here, 1 minus, our CDF is 1 minus e to the power of negative 8,000 divided by 1,000, right? And so here we can do some simplification. This 1 is going to subtract out with this 1, and so that's going to leave us with e to the power of negative 8,000 divided by 1,000, which is e to the power of negative 8, right? And we can write that as about 0.00034. So the probability that x is greater than 8,000 is about 0.00034. Okay. If we wanted to sort of ask a more straightforward question in the sense of it's something we've already seen, right? Probability x is between 7,500 and 12,000, right? So what's the probability that x is in the interval from 7,500 up to 12,000, right? This is always going to be f of 12,000 minus f of 7,500. Okay, and so now it would be a matter of plugging both into our CDF here, right? So that's going to be 1 minus e to the negative 12,000 divided by 1,000 minus 1 minus e to the negative 7,500 divided by 1,000. Okay, and now we can do some simplification. This 1 will cancel with this 1, and then we get e to the negative 7.5 minus e to the negative 12. And if we work out what that is with your calculator here, you should get that it's about 0.006. No, sorry, an extra 0 there. 0.006. Okay, and so that's the probability that x falls between 7,500 and 12,000. Okay, and so using the CDF is going to be the key tool for us calculating probabilities with continuous random variables. And it's a little bit weird because we need to remember that the probability it takes on any specific value is always going to be 0. However, once we're working with the CDFs, sort of all of the techniques we're used to using are still going to hold, right? We're just thinking about intervals rather than points now. Okay. Now, despite the fact that the CDF is going to capture sort of all of the behavior of the random variable that we might care about, it's not really a direct parallel to the probability mass function, right? The probability mass function is nice because once you know it, you know sort of the behavior of the random variable entirely. You know what is it like to do around particular values, around specific points. Okay, and so with the continuous random variables and with their cumulative distribution function, it gives us the tools to calculate probabilities, but you can't read off sort of the properties that you might want to know, right? You can't look at a CDF and immediately know how likely is it that this is going to be around the value of 1. Okay, and so because of that, we want sort of another tool that's not going to tell us what's the probability that x equals any particular value, right? Because we know that that's always 0. But we might want to know how likely is it that x is near a particular value. And that's going to bring in what we'll call the probability density function here. And so we're going to write this as a lowercase f of x, right? So it's still a mathematical function. And what this is going to tell us is this is going to be the relative likelihood of the random variable x being near the small value that we plug in, right? So how likely is x to be around 1/2, right? And I'll make a note here in the notes, right? But the probability that x equals any specific value is not the CDF, it's equal to 0, right? So that's not in general going to equal f of x. So this isn't a probability function. However, it does give us sort of how likely comparatively are values, okay? And so how might we think about this in sort of an intuitive sense? Well, we know that in order to talk about probabilities that are meaningful with a continuous random variable, we have to be thinking about intervals, right? And so we can think about our number line here again, right? And suppose that we have some value here in the middle, which we'll call x, right? And we want to know what is the probability that we're around this value here. One thing that you might think to do is to draw an interval around x here, right? So maybe this is like, I don't know, x minus 0.01, and then this is x plus 0.01, right? And if you look at that interval, we know that you can calculate the probability that you're here using our sort of CDF differencing trick, right? And that's going to tell you how likely are you to be around x in some sense, right? But we could do better, right? We could come in here and we could draw it on this interval, or we could draw it around this interval, or we could zoom in even more and go around this interval, right? And as you get closer and closer and closer, right, then you're going to get closer and closer to giving a probability that you're at the value of x. And so what we can sort of think about is that the PDF, or the probability density function, is going to sort of be a measure of how likely are you to be in these increasingly small intervals around the value that you care about. So if we think about sort of taking x minus delta to x plus delta, right, where delta is a very small number, then what the PDF is sort of giving us is the probability that x is in this interval, x minus delta, x plus delta, is going to be equal to 2 times delta times the PDF, okay? And if you take a calculus course, there's sort of a reason that this is going to emerge as a sensible definition here, okay? And so we'll not be talking about that in our class, but the idea is that, this 2 delta, we can just think about as being some very small number, right? And so it's essentially going to be telling us how likely it is, scaled up or down, to be around the value of x. Okay, and so that's sort of just a little bit of intuition about what the PDF is actually measuring for us. But it's important to remember the PDF is going to give us this sort of relative likelihood. High values for the PDF are going to give us more likely values. Low values for the PDF are less likely values. And ultimately, though, it's not giving us specific probabilities. Okay, so you can't look at the PDF and know this is a particular probability. So what can we do with PDFs then? Okay, and so we'll sort of think about two possible options to use PDFs for here, and then those will sort of start to be useful tools for us moving forward. So the first thing to just point out with this plot, right, is that we have the plot of three different PDFs here. We have this sort of constant line here, and then we have our sort of bell curve looking shape, and then we have this decreasing one in black. Okay, and so all of these questions are asking us which PDF or which random variable that's represented by one of these PDFs is most likely to be around particular values. Okay, and so we can first go through that, because what we know is that the higher the PDF for any particular value, the more likely it is that the random variable is around there. And so if we look at the value of 1 on our plot here, right, so 1 will fall somewhere here. What we know is that this PDF up here is going to be the highest, and then this PDF right here, and then this PDF down here, right? And so the random variable represented by the black PDF is going to be highest around 1. If we go around 6 instead, and we can do the same thing, go up to here, and we can see that at around 6, the blue PDF is going to be the highest, and so that's the random variable that's most likely. If we come over to 14, right, it's this one right here, which is going to be our red PDF. We're also asked this question, what is most likely to be exactly 10? Okay, and so we should think about this for a second before I give away the answer, right? But the important thing about asking us the exactly 10 here is that we're not looking about being near the value. In order for it to be exactly 10, every continuous random variable is going to have exactly probability 0 for all 3. Okay, and so one thing that you can do with PDFs is you can plot out your PDF and then you can compare them, right? Or you can just look at it and say, okay, well, so for this blue PDF, this bell curve looking one, right, we know that it's sort of most likely up here, and then it's going to be a lot less likely over here or over here. Okay, and so that's one useful technique, is it just sort of shows us where are we expecting to see values in a very real sense. The other thing, and we're going to start using this when we start talking about a specific distribution for our random variables, but is that the plot of the PDF also is sort of capturing probabilities of intervals in a very particular kind of way. And so in order to actually calculate this directly, you'd need to take a calculus class. And so if you've taken a calculus class, this might seem familiar, but in general, if you were able to work out what is the area under a curve between 2 points, right? So if we think about this area that I'm highlighting in here, and I'll highlight in this full space right here, sort of in this pink color, right? This space that I'm highlighting, if you were to work out how much area is there in this highlighted region, that area is going to equal the probability that x falls into that region, right? So the area is the probability that x is, in this case, between 8 and 12. And so another very useful reason for plotting out these PDF functions here is that if you can start to think about how much area there is under the curve in particular spots, that tells you specifically what is the probability that x falls into those regions. Okay, and so what we can say is that if you look at something like the blue curve down here, and we think about this area that I'm highlighting in over in the tail down here, okay, this is a very small area, right? And so it's very unlikely for x to be there, especially if you were to compare it to, for instance, this same type of area in red, where this is much larger, right? I've colored in a lot more space there, and so we know that it's a lot more likely for x to be between 0 and 2 with the red curve than with the blue curve. All right, and so those are the two sort of or three most useful features of plotting out the PDF for us, right? And so we'll use all of those to sort of great effect as we move forward. Now, when we were introducing discrete random variables, we saw that there were several different named distributions that we were thinking about. With continuous random variables, there's going to be sort of an equal number of named distributions, but we're really not going to focus on all of those because really only one is going to matter a whole lot for us. But we'll introduce two just to sort of see how they're useful and then sort of go from there. Okay, so the first named distribution that we want to introduce is what we'll call the continuous uniform distribution. Okay, and so a random variable is continuous uniform, and this is going to be sort of the continuous analog to the discrete uniform that we were looking at before. But a random variable is said to be continuous uniform if it is a continuous random variable, right? So that sort of goes without saying for the definition, but I'll include it here to help differentiate it from what we've seen before. So it's a continuous random variable which is equally likely on some interval. And so when we're thinking about it being equally likely on some interval, right, we're thinking about something like that bus example that we were looking at before, where the bus was equally likely to show up anywhere in the next 15 minutes. And so what we're saying is it's equally likely on the interval 0 to 15. Okay, and so anytime that a random variable is equally likely on some interval, we say that it's a continuous uniform distribution. And actually, most often, we're just going to say it's a uniform distribution. So if it's not clarified, we're thinking continuous uniform. It's going to have two parameters, and it's actually the same two parameters that we had in the discrete case. So A is going to be the lower bound of the interval, and B is going to be the upper bound of the interval. And so what we're really saying here is that X is going to fall between the values of A and B, right? And that's what we sort of know here. We can think about the probability density function as being a known function here, right? And so with a discrete uniform, or with a continuous uniform, sorry, we're looking at f of x being 1 over b minus a, and this is going to be valid for all x in the interval a to b. All right. We can also write down the CDF of this, okay? And the CDF is always going to be x minus the lower bound divided by b minus a. Okay. And so that's going to give us our CDF on the interval here. Now, we haven't talked about this because we actually don't have the tools for calculating them directly. It requires some calculus knowledge. However, there's going to be expected values and variances for continuous random variables as well as medians and percentiles and interquartile ranges and all of that good stuff. We're not going to be able to work these out by hand for the most part. However, it is useful to know these things as well. And so with the name distributions, they're going to be sort of given just like they were for the discrete case. So we know that the expected value of x, if it's a continuous uniform, is going to be a plus b over 2. Okay, so it's the halfway point of the two, which sort of makes some sense. And the variance of x is going to be b minus a squared divided by 12. Okay. And so with all of that, that sort of captures the behavior of a continuous uniform distribution. And once we have all of this, we can basically use it in exactly the same way that we were using all of the named distributions for the discrete case, right? So you can identify that something is a continuous uniform, and then you can use these functions as given. So we can say, suppose that x is a continuous uniform, right? So remember that this tilde notation here, right here, means that we have x follows the distribution, right? So this is sort of saying that x follows a uniform distribution with parameters 0 and 15. What is the expected value and the variance of x? Okay, and so what we need to know is what are the two parameters here. So we know that a is equal to the lower bound, which is 0. and b is equal to the upper bound, which is given as 15. And then as soon as we know this, we know, well, the expected value of x is going to be a plus b, which is 0 plus 15 divided by 2. So that's going to be 7.5. And the variance of x is going to be b minus a, so that's 15 minus 0 squared divided by 12, right? Which is, if you plug into your calculator, 18.75. Okay? And so we can sort of use this in much the same way that you can use the results from the discrete case. Okay? Now, the continuous uniform does come up sometimes, but it's not the most important distribution that we're going to be thinking about. The most important distribution that we're going to be thinking about is the normal distribution. Okay? And so the normal distribution is far and away the most important distribution in all of probability and statistics. It's not even really close at all. In fact, it's such a common distribution that you definitely have heard of the normal distribution, whether or not you're aware that you have. Okay? And so how do we know if it's going to follow a normal distribution? In this case, it's a little bit less sort of well-defined compared to some of the other examples we've seen. But what we can say is that it's going to follow a normal distribution if it follows a bell curve shape. Okay, and this is a little bit sort of loosey-goosey, okay? But the idea is that anything that's following a particularly well-behaved bell curve shape is going to be normally distributed. And so what might we be thinking about here? Well, there's plenty of examples in the real world. So we could think about something like heights. The common example with bell curve is going to be the grades in a classroom or sort of in a degree program. Okay, we might think about someone's reaction times. Okay, so if you measure reaction times, those are going to be distributed as a bell curve here. If you're in a lab setting and you want to know how much error there's going to be in the measurements you're taking, those are going to be approximately normally distributed. So we can say measurement error. Tons and tons and tons of other options are going to be distributed as a normal distribution here. Okay, and so the idea is that the normal distribution is going to be this really nice looking bell curve shape. And any time that you've ever seen a bell curve come up, it's probably been a normal distribution. And so what am I thinking about with this bell curve, right? I'll try to draw it out. We're going to be drawing out a lot of these throughout our course. I'm not particularly good at drawing them, but that's okay. It sort of gives the idea, right? So this is the idea that in the center, we have sort of the highest peak, right? And then it's going to be symmetrically distributed around both of these, okay? So there's a nice symmetry here on both sides. Above the center and below the center are exactly the same. So every normal distribution is going to look like this bell curve, but we have some parameters to define specifically what bell curve are we dealing with. Okay, and so the two parameters we're going to be thinking about are going to be mu, okay, and mu is going to be the mean or the expected value, right? So it's literally what is the expected value of the distribution. And the variance, which we'll denote as sigma squared here, right? So it's this Greek letter sigma squared is going to be the variance. And that is, again, literally the variance of x. I will also note that sometimes you will see this as sigma being the standard deviation. And if we remember back to when we defined standard deviation, the standard deviation, or the SD of x, is equal to the square root of the variance. Right? And so the notation makes sense because what we're saying is that sigma is equal to the square root of sigma squared, right? And this is true sort of by definition. Okay. Now we write down x is going to follow a normal distribution with some mean and some variance. So with mu and sigma squared, where you can plug in the values there. And what I'll point out about this bell curve over here is that mu is going to be the center line, right? So we're always going to be centered on mu. And then the variance, you're going to be able to see by how spread out this is. So the spread here is going to be sort of related to our variance. Okay. And the higher the variance, the more spread out it's going to be, which sort of means that it's flatter. If you have a lower variance, it's going to be sort of more smushed in, which means it's going to be taller. Okay. And we'll see sort of examples of that. Now, the probability density function I will write down. We will never need to use this directly, but it's perhaps good to see it at least once. So the probability density function is going to be equal to 1 divided by the square root of 2 pi times by sigma. Then multiply this whole fraction by the expected, or not the expected value, the exponential of negative x minus mu squared divided by 2 sigma squared. Okay, so this is our probability density function. It's a mess. It's not sort of a nice function to look at. We won't need to be manipulating this a whole lot, but it is good to sort of have it in your back pocket in case it ever comes up. As big of a mess as the probability density function is, we can at least actually write it down, right? The same can't be said for the cumulative distribution function. So we are not able to write this down. Okay, and so this sort of presents a problem for us where we can't sort of express in mathematical notation the cumulative distribution function. What we'll see in just a little bit is that we'll often sort of be bringing in new notation to talk about the cumulative distribution function for the normal distribution here, right? But in sort of our standard notation, we're not going to be able to sort of represent it using nice closed form expressions of different values, okay? And so instead, we're going to be sort of just thinking, well, the cumulative distribution function will still represent probability that x is less than or equal to x. What I will say is that in sort of the modern world, computers can calculate all of these values for us, right? So we don't actually need to be able to represent this in algebraic notation, because ultimately, if you needed to know what's the probability that a normal is less than some threshold, you could look that up on your computer very quickly. And so that's sort of how we're going to get around this. Now, the point that I'll emphasize is that the normal distribution is going to sort of follow the sort of standard bell curve shape, right? And so we saw this before, but it's worth drawing out again, and then just sort of pointing out some of our features of it, right? And so the first idea is that we're centered on mu, okay? And then what we know is that this is going to be symmetric, right? We sort of pointed this out before. And so the idea is that if you were to take sort of some value here, which is say mu minus a, and then you take some value here, which is mu plus a, right? And we go up to our bell curve on both sides, this value and this value are going to be equal. Okay, and so that's what we mean by being symmetric, right? But sort of what we can think about then, right, is we were talking about how the area under curves gives us our probability. And so if we think about the area that's under the curve, sort of mu minus a over here, or we think about the area that's under the curve mu plus a over here, right? So we go off to infinity in both directions there. This area and this area, by symmetry, the area is the same. And so therefore, the probability that x is less than or equal to mu minus a has to equal the same as the probability that x is greater than or equal to mu plus a. Okay? And so this type of thing where there's this symmetric behavior means that if we can figure out how to calculate, for instance, the probability that x is less than or equal to mu minus a, then we can calculate any probabilities on the other side of the distribution as well, just by asking ourselves, where is sort of the corresponding area? Okay, and so these symmetry tricks are going to come up a lot, and we'll see them as we start to use the normal distribution a little bit more. Okay, now, because there's sort of such a common use of the normal distribution, and because we can't express it in a nice closed form solution, it's important for us to be able to still sort of manipulate normal random variables. And so in order to do this, we're really going to focus in on one specific normally distributed random variable, and that's the idea of the standard normal distribution. And so what we'll say is that z, and we almost always use z as the standard normal variable here. So z is standard normal if z follows a normal 0, 1 distribution. Okay, and so if z is a normal distribution which has a mean of 0 and a variance of 1, then we say that it's standard normal. Okay, and if z is standard normal, then we actually define some new notation for the CDF of z. So we say the probability that z is less than or equal to some specific value is going to be equal to this notation here, which is the phi. It's a capital phi, phi of z. Okay, and so this right here is new notation. When you were thinking back to sort of high school and you started to learn trigonometric functions, and we saw that, the ratios of angles in a triangle are going to be similar, right? Then you may have seen, for instance, the cosine function or the sine function or the tangent function, right? And we introduced that as sort of new notation. You could say sine of an angle is equal to sort of the ratio of the lengths there, right? You can think about phi in much the same way, right? Or you could think about it in much the same way that you think about a logarithm, right? So it's this mathematical function. Our computer knows how to calculate phi of any number that we plug into it, right? But mathematically, what it represents is the probability that a standard normal variable is less than or equal to some thresholded value, okay? And so we can sort of introduce this as new notation, and then instead of needing to have a CDF that we can express in closed form, instead, anytime we need to write down that CDF, we're going to write down phi of the value, okay? And so that's sort of how we're going to end up using these normal random variables. So the reason that we're going to care about the standard normal variable is because any normal random variable can be converted into the standard normal. And this is going to happen through a process that we're going to refer to as standardization. Okay? So if you want to standardize a normal random variable, then the idea is you want to take it and make it into something that has the standard normal distribution. And so specifically, if we have x, which is normal with a mean of mu and a variance of sigma squared, then what we can do is we can take x, we can subtract off its mean, and we can divide by the standard deviation. So we divide by sigma. And it turns out that if you do this, no matter what mu and sigma are, this is always going to have a standard normal distribution. So to put this in words, if you subtract the mean and divide by the standard deviation, then you are left with a standard normal random variable. Okay, and so this sort of might seem interesting, but the question becomes, how can we use this effectively? And the idea is that now, through sort of both this standardization process, as well as through the notation that we just derived around the CDF of a normal standard normal, what we're going to be able to do is we're going to be able to convert any probability that we want to talk about with x in terms of phi. Okay, so how might we do this? Well, if we just say x is a normal with a mean of mu and a variance of sigma squared, what is the probability that x is less than or equal to x? Okay, and so let's think about this event here. We have x being less than or equal to some particular value. Now, note that if I take x and I subtract off mu, this is the same now as being x less than or equal to mu, right? All I've done is I've subtracted mu on both sides, and that's totally valid. That doesn't change anything about what we're doing here. We've done the same thing to the left-hand side as we have to the right-hand side. We can also now divide by the standard deviation. And this is important to note because the standard deviation is always a positive value, right? So this isn't going to change anything either, right? You're just doing the same thing to the left-hand side as you are to the right-hand side. But what we know is that this value right here is going to be sort of z, right? It follows a normal 0, 1, right? And this is just some number. And so what we can do is we can take this same process right here and apply it to our probabilities. Okay, so what we're saying is that the probability that x is less than or equal to some value x has to equal the same thing as the probability that x, and I'll just erase that underline there, x minus mu divided by its standard deviation has to be less than or equal to x minus mu divided by the standard deviation. But we know that the left-hand side here, we can just express as z, right? So it's the probability that z is less than or equal to this. And z is the standard normal, and so its CDF is going to be equal to phi of x minus mu divided by the standard deviation. Okay, and so what we've done here is we've converted a question about an arbitrary normal into a statement about the standard normal. Okay, and this is going to work no matter what x happens to be. Okay, and so we can see this sort of in practice with some more specific, some more concrete examples here. Right, so what we're doing is we're taking x to be a normal with a mean of 90 and a variance of 100, and y is going to be a normal with a mean of 110 and a variance of 400. And so we can ask these questions. What's the probability that x is less than or equal to 80? And there's two sort of approaches here, right? The first is that we could take this relationship that we've derived up here, and we could say, well, the probability that x is less than or equal to 80 has to equal phi of, and then we take 80 minus the mean, which in this case is 90, divided by the standard deviation, right? And so this right here is sigma squared. And so then sigma has to be equal to 10. The square root of 100 is 10, right? So 80 minus 90 over 10. So that's going to be phi of negative 1. Okay, and so that's sort of one way that we could do it, is just use the formula. If you didn't want to use the formula directly, then we can also just work through that same process directly, right? So we can say, well, the probability that x is less than or equal to 80 has to be the same thing as saying the probability that x minus its mean, right? Its mean is 90, divided by its standard deviation, which is the square root of 100, has to be less than or equal to 80 minus 90 divided by the square root of 100. Do the same thing to the left-hand side and the right-hand side. Okay, but now this is the probability that z is less than or equal to, and we're going to get negative 10 over 10, right? And from here, we can fill in phi of negative 1. It's exactly the same process. It's just sort of a matter of, do you use the formula directly or do you work it out by hand? Okay. We can do a similar thing here with probability that y is greater than or equal to 125, right? So the probability that y is greater than or equal to 125 has to be equal to, and then again, we'll use the tricks that we know here, right? So that's going to be 1 minus the probability that y is less than or equal to 125, okay? And now we can use sort of our results from above, right? Because y is a normal, and so what we can say is, well, this has to be 1 minus phi, and then it's 125. The mean of y is 110, divided by the standard deviation, which in this case is the square root of 400, okay? And so that's going to be 1 minus phi of, I believe, 0.75. Okay, and then again, we can leave it in this form because if you had your calculator, you had your computer, you could actually work out that as a number. Not all of your calculators are going to be able to compute that. Many of them will, but not all of them. But everyone's computer could do this. Okay, and so that's sort of how we can use this process of standardization to actually work out sort of probabilities as they relate to arbitrary normal random variables. Okay. Now, I will point out now, and we will revisit this in a little while. And so I just sort of want to give out this definition. We'll see it in the coming lectures, but it's this idea of normal critical values. And the idea is that because we're always working with the standard normal CDF, right? Because we're always thinking about phi as the main point of contact for our probabilities related to the normals, there are going to be particular values that we could plug into phi to get specific values out of. And so in particular, we can think about this as generating a specific relationship where we could say phi of z alpha is equal to alpha, okay? And then certain values for alpha slash z alpha come up a lot. And so one example that we might look at is that phi of, say, 1.96 is going to be approximately equal to 0.975. Okay, and so what we can say here is that z of 0.975 is going to be equal to 1.96. Okay, and so we don't need to exactly know why we care about 1.96 right now, right? But the idea is that what we're going to start doing is identifying some of these critical values, and that's really going to help us with our calculations going forward. We will revisit this in a couple of chapters now, so it's sort of, file this away. Remember this, it will come back up again, but I just want to sort of start this idea here so that we can be thinking about it moving forward, okay? Now, I want to introduce what we will call the empirical rule for the normal distribution, okay? And the idea with the empirical rule is that the fact that every normal distribution follows the same sort of predictable pattern is going to be very, very useful for us in general, right? What it's going to allow us to do is use the same types of behavior no matter what normal distribution we're working with, right? We sort of already saw this with standardization, where it doesn't matter what the normal distribution is, we can always standardize it, work with a standard normal instead. There's going to be what we'll call the empirical rule, which is sort of a rule of thumb or sort of a way of thinking through some problems, which is going to enable us to fairly quickly calculate probabilities that have to do with events that we might care about. And we're going to be able to do this sort of for any normal distribution. And so there's sort of two ways of thinking about the empirical rule. There's the graphical way, and then there's sort of the algebraic way. And so I'll start with the graphical way, and I'll draw this out. And the idea is that with the empirical rule, what we want to be able to do is capture some common events that we might be thinking about, right? And so we know that this is mu, but I'm going to mark off mu minus sigma, mu minus 2 sigma, and then mu minus 3 sigma. Okay, and of course this keeps going beyond mu minus 3 sigma, but for the empirical rule, we're only going to be concerned with up to mu or minus 3 sigma, and then we can mark out the symmetric points above. Okay. And what we're going to try to do is give ourselves sort of approximate probabilities that have to do with events of intervals that fall in these ranges. And so we can think about the fact that our bell curve is going to look something like that, right? And then we might be interested to ask ourselves, well, what's the probability that we fall between mu minus sigma and mu plus sigma? Right? So what's the probability that you're within one standard deviation of the mean? Okay, and what we know, or what we saw, was that this probability is this area under the curve here. And it turns out that it doesn't matter what mu or sigma are. The probability that you fall into this region of the curve is always going to be the same. And this is going to be approximately 68%. Right, so there's an approximately 68% chance that you're going to be between minus 1 sigma and plus 1 sigma. Okay. And the thing that I'll point out here is that we know how this is also going to be divided because of symmetry. We know that there's going to be 34% chance that you're between sigma and mean. And then there's going to be another 34% chance that you're between the mean and +1 standard deviation. Okay. And so this is going to give us sort of the first piece of the empirical rule here. But we can ask the same questions about the other marks here, right? So what's the probability that we're between 2 sigma below or above the mean, right? And so that's going to give us sort of this whole area here, right? So we can shade in here, and then it's going to cover through, and I'll just sort of put some marks through here just to indicate that, but then it's also going to be everywhere down here. And if we work out what that is, again, it doesn't matter what normal distribution we're dealing with, this will always be approximately 95%, right? And so then again, you're going to have 95% over 2 half on the lower half and 95% divided by 2 on the upper half. If we go to sort of the final point, right, what is it between -3 sigma and +3 sigma, right? And so we can highlight this area in, we'll do this in sort of this yellow color. And again, I will just indicate that we are coming through this whole region, right? And then we go up to here. And this between -3 and +3 is going to be about 99.7%. Okay. And so what we're saying here is a few things. The first is that there's this nice predictable pattern, and we're going to be able to use this predictable pattern to answer some probability questions about the normally distributed random variables. But what we're also saying is that almost everything we observe is going to be between -3 standard deviations and +3 standard deviations of the mean. There's a 99.7% chance that the event that occurs is within that range, right? Which means that there's only a 0.3% chance that you observe something outside of that range, right? So that becomes very rare very quickly. And if you had gone to 4 and 4, you'd see that that's even stronger. And so the idea with this is that it both sort of gives us a quick way of sort of approximating some of these probabilities. And I will point out these are just approximations, but they're pretty close. But it also is going to sort of indicate to us the sort of well-behaved nature of normally distributed random variables to begin, right? So they're all going to sort of be tightly clustered around their mean in a way that's very useful for us. The other way that you might see this sort of being expressed is just, you can list out these probabilities directly. Okay, so we can just say that the empirical rule tells us that the probability that mu minus sigma is less than or equal to x, which is less than or equal to mu plus sigma, this is going to be approximately 0.68, right? The probability that mu minus 2 sigma is less than or equal to x, which is less than or equal to mu plus 2 sigma, is going to be approximately 0.95. And we could say the probability that mu minus 3 sigma less than or equal to x, less than or equal to mu plus 3 sigma, is going to be approximately 0.997. Okay, and so this is sort of going to be a more compact way of representing it. I think generally the graphic is useful when we're trying to answer questions relating to this, but the sort of just algebraic statement here is going to be a nice way of summarizing that graphic. Okay. And so then how might we use this in practice? Well, we can ask these types of questions that we were looking at before, right? And we can sort of see how the empirical rule is going to be useful for us in answering these questions. And so we have x is falling between 88 and 30, or it's a normal distribution with a mean of 88 and a variance of 36, and y is a normal distribution with a mean of 124 and a variance of 324. And so what is the probability that x falls between 70 and 106? And we're being asked approximately, okay? And so the question for us is always going to be, well, how many standard deviations away from the mean is this value, right? So if we think about 70, right? 70 is not sort of a number that we have written in our empirical rule anywhere. But what we want to do is we want to say, well, 70 is going to be equal to mu plus k sigma for some value of k. All right. And what we know is that mu right here
is equal to 88, and sigma is going to be the square root of 36, which is 6, right? So we can say here sigma is going to be equal to 6. And so if we fill that in, right, we'll say 70 is going to be equal to 88 plus k times by 6, okay? And so then we could just solve what is k here, okay? And so we can do this. We can say, well, k is going to be equal to 70 minus 88. We subtract off the 88. We have to divide by the 6, right? And so that's going to be negative 18 over 6, which is negative 3. All right, and so k is going to be negative 3. Okay, so that's the first piece, and that's for our lower bound here. What about our upper bound? Well, 106 is going to be mu plus k times sigma, right? And so that's going to be 88 plus k times by 6. And so if we do the same thing, k is going to be 106 minus 88 divided by 6, which is going to be positive 3. And so what we're asking here is, what is the probability that mu minus 3 sigma is less than or equal to x, which is less than or equal to mu plus 3 sigma, right? And we know from the empirical rule directly that this is approximately 0.997. Okay, and so the empirical rule immediately gives us that this is 99.7% approximately. Okay, and so that's sort of the most basic application of this, right? We can work out where is this sort of range that we're looking at, and then how does that relate back to the empirical rule. But we can also see examples like the following, which is not necessarily as clear. So if we do the same thing, right, now we're looking at with y instead of with x. And so with y, mu is going to be 124, and then sigma is going to be the square root of 324, right? So sigma is the square root of 324. Okay, and so this is 18, I believe, right? And so what we have is, let's say 70 is equal to mu plus k sigma. Okay, and now we would fill in our values for mu and sigma here, right? And so we're going to have 124 plus k times by sigma is 18. And then we can do the same thing. So k is going to be 70 minus 124 divided by 18, which should give us negative 3. Okay, so we get a negative 3 on the 70 as well. But then if we do the same thing for 106, right, 106 is equal to mu plus k sigma, which is going to be 124 plus k times by 18. So then k is going to be 106 minus 124 divided by 18. This is going to be negative 1. And so what we're asking here is, what is the probability that x minus 3 sigma is, or sorry, not x, mu minus 3 sigma is less than or equal to x, which is less than or equal to mu minus sigma. And the empirical rule does not immediately tell us what this answer is, right? And so we have to sort of think about how we can use our empirical rule to answer this question. And so what I'll do is I'm actually just going to copy in this graphic to the next page here, prevent us from having to sort of draw it out again. Though I would advise that you get sort of quick at drawing these. They become very useful for us to answer these types of questions. But I should be able to sort of shrink this down. And we can start thinking about how can we answer this question here, right? And the idea that we can sort of rely on is that while we do not have a statement from our empirical rule directly to fall between -3 and -1, what we do know is that there's a sort of certain symmetry to things, right? And so the area that we're thinking about is we want to be -3 sigma, right? And we have to be above that, but we want to be below -1 sigma, right? And so we want this total red area here. Okay. And so we can sort of think about how are the different ways that we might think about creating this red area. And as soon as you can start thinking about how can you create this red area, right? Then we can think about, okay, well, that's going to be a particular way for us to sort of get to this. And the point that I'll make to create this red area, right, is that if first we were to think about the between -3 and +3, right? We know that that's 99.7%. Okay. And what we know is that that's 99.7 if you divided it by 2, right? So if you divide this 99.7 by 2, then that's going to give you how much is on the upper side and how much is on the lower side. 99.7% divided by 2. Okay? And so there's 99.7 over 2 below the mean, 99.7 over 2 above the mean. And so we're not down to the red shaded area, but what we are down to is 99.7% over 2 gives us just this region between mu minus 3 and mu. And then what we know is that, okay, well, if you were to take that region and you remove out this area that we have right here, which I'll just highlight in over top of our other highlighting already, right? So that area that we've sort of double highlighted there, then you're left with just the red region, okay? And what we know is that this region right here, right, this region is going to be equal to our 68% divided by 2, right? Or as we have labeled already, that's 34%. And so what we're saying is that if you take this 99.7 over 2, so 0.997 over 2, and you subtract off 0.68 over 2, that's going to give you the area that we need, right? And if you work this out, you should find that that's 0.1585, okay? And so what we're saying is that this region that we care about here is going to be 0.1585, which we can get because it's the difference between sort of this half and this square right here. Okay. And so what I would encourage you to do when you're faced with these problems is to draw out this picture. And then as soon as you draw out the picture, you can start to say, okay, how can I make up the area that I actually need? All right. And that's going to be sort of a useful way of getting there. And with a little bit of practice, that breaking up becomes a lot sort of more standard for us. Okay, so the empirical rule is very useful for us because it gives us this quick way of doing some approximate calculations based on the normal distribution, but it only works for the normal distribution. Okay, and so I want to just sort of introduce this idea of Chebyshev's inequality. Okay, and what Chebyshev's inequality is going to do is it's going to give us statements like what we get for the empirical rule, except these are going to hold for any x. All right, and so what we can say is that the probability that, and if we think about the statements that we're making for the empirical rule, we're always looking at mu minus k times sigma being less than or equal to x, which is less than or equal to mu plus k times sigma. And what Chebyshev's inequality is going to tell us is that this is always going to be greater than or equal to 1 minus 1 divided by k squared. All right, and this holds for any x and k. Now, the important thing about it holding for any k is that it doesn't have to be for whole number values for k, right? So it could be for k equals 1.5 instead, right? And so that's sort of an advantage to it. But I will point out two things about this. The first is that this doesn't actually give us probabilities. It gives us a lower bound on the probabilities. It tells us that the probability has to be larger than a particular value, right? It doesn't tell us that the probability is going to equal any particular value. All right, so that's the first point to make there. The second point is thinking about what would happen if you were to take, for instance, k equals 1. All right, so if you take k equals 1, then you get mu minus sigma, mu plus sigma, right? And if you plug in k equals 1 into the expression there, you're going to get 1 minus 1 divided by 1. So that's 1 minus 1, which is 0. So all we're saying is that the probability is greater than 0. So that's not very useful. Now, if you plug in a value larger than 1, you're going to start to get things that aren't exactly equal to 0, right? And so that's where it becomes sort of a little bit more handy. But it's a lot less useful of a tool for us. The big benefit is that it's always going to hold. You don't have to worry, are you dealing with a normal or are you not dealing with a normal? And so because of that, Chebyshev's does come up on occasions, and so we'll sort of see how we might be able to use it here. But it's going to come up a lot less than the empirical rule is, just as a general rule. So we have this example where x is going to be sort of any random variable. We don't know the distribution. And what we're told is that the mean is 88 and the variance is 51.84. And then we're asked, can we be 90% certain that x is going to fall between 70 and 106? Okay. And so because we don't know the distribution and we're being asked a probability, and what we're really being asked is about a lower bound on a probability, right? Can we be at least 90% certain that x is going to fall between these values? That's saying, is x going to fall between these values with greater than or equal to 90% likelihood? And so because of that, we know we're dealing with this Chebyshev's sort of question here. And so what we need to be able to do is make this into a statement of the form probability mu minus k sigma less than or equal to x less than or equal to mu plus k sigma. And so what we want to know is probability that 70 less than or equal to x less than or equal to 106, right? But what we want to be able to do is we want to be able to write 70 is equal to mu and then say plus k times sigma for some value. And we'd want to write 106 as mu plus k times sigma for some value, right? And remember, mu is 88, sigma is 51.84. And so if we take this, we take 88 plus k times by 51.84, and we take this as 88 plus k times by 51.84. And if you solve for k in both cases here, using the exact same process we were looking at before, what you should find is that k is going to be equal to negative 2.5, and k is going to be equal to 2.5. Okay, so this is sort of perfect. We're in this situation where what we're asking is, what is the probability that mu minus 2.5 times sigma is less than or equal to x, which is less than or equal to mu plus 2.5 times sigma. And we know from Chebyshev's that this has to be 1 or greater than or equal to 1 minus 1 over 2.5 squared. Okay, and if we solve that, 1 minus this, that's 0.84. Okay. And so what we're saying is that we know the probability that x falls between these two values is going to be at least 84%. However, that's not 90%, right? And so no, we are only 84% confident. Okay. Now, if you had been able to use the empirical rule and you could sort of work through this yourselves, you would find that actually with the empirical rule, you're going to be over 90% certain. Okay. But with the Chebyshev's inequality, we're not going to be able to. So if we don't know that this is normal, we can't say for certain that it's going to be greater than 90%. All right. Now, we've seen sort of some nice properties of the normal, right? That can be standardized. We can just work with the standard normals instead. There's also some important properties, which we'll call the closure properties of normal. Okay. And the idea with the closure properties of normally distributed random variables is that if you take any two normals and you add them together, you're still going to get something that's normal. I'll point out that if we go back to where we were talking about the process of standardization, I'll make a note over here that this tells us that if you multiply by a constant or you add a constant, things are still normal, right? So if x is normal, then ax plus b is also going to be normal, and it's going to be normal following the patterns that we have outlined for our mean and our variance transitions here, right? So a mu plus b, and then a squared sigma squared, right? And this relies on the expected value of ax plus b and the variance of ax plus b. So those are worth reviewing if you don't remember those, right? But in general, we know that if you take a normal and you multiply it by something and then add on stuff, it stays normal, right? And the same thing is going to happen if you take two normals and add them together, okay? And so in general, x plus y is going to follow a normal distribution where you have the mean is mu x plus mu y. the variance is going to be sigma x squared plus sigma y squared plus 2 times the covariance between x and y, right? And then if x and y are independent, which is sort of the case that we're going to care about the most, if x and y are independent, then the covariance of x and y is equal to 0, right? We saw this in lecture. And so then therefore, x plus y is going to follow a normal distribution with a mean of mu x plus mu y and a variance of sigma x squared plus sigma y squared. Okay. And so we can sort of extend this out, right? So if we take this, instead of just thinking about x and y as being independent normals, we can think about x1 through xn as being independent normals, right? And so if we think about the summation, right, then we're thinking about x1 plus x2 plus and so forth up to xn. And what we can say is that this is going to be normal with a mean of mu1 plus mu2 plus up to mu n. Okay. And then you can do the same thing with their variances. Sigma 2 squared plus up to sigma n squared. And so this is going to be what we will call the closure properties. And the idea is that it's very nice for us to know that if we're adding up a bunch of normals, what the thing that we're getting out is still going to be a normally distributed random variable. Okay, that's not going to happen with every distribution. In fact, it doesn't typically happen. And so because of that, because we know that things remain normal, that's going to be quite useful for us, right? And so these are all sort of the toolbox that's arguing why we should care about things being normally distributed. And it's going to be because they're well behaved, because we can use things like the empirical rule to approximate their probabilities. It's going to be because they arise a lot in nature. They're going to arise a lot sort of in mathematics as well. And they have sort of these nice properties that allow us to work with them, right? We can standardize them. We know that if we're dealing with multiples, we're going to be in a case where it stays normal. Everything's going to stay normal. There's really one last property that we'll look at of normals that is going to be sort of a useful property for them for ours. And that's going to be the fact that the normal distribution is going to be useful for approximating other distributions. Okay, and so we saw when we were looking at discrete distributions, the binomial distribution, right? So x is binomial NP, right? And so just to recap, we know that if x is binomial NP, then the expected value of x is n times p, and the variance of x is n times p times 1 minus p. Okay? And so the idea is that if n is going to be a large enough value, then this binomial is going to be approximated well by a normal distribution with this mean and with this variance. Okay, and so we'll write this out. If n is large, then x is approximated well by, say, w, where w follows a normal distribution with parameters np and then np 1 minus p. Okay, and so what we mean to say here is that the probability that, say, x is going to be less than or equal to some particular value should be approximately the same as the probability that w is less than or equal to some value. Okay. Now, there is one sort of catch to doing this, and that's this idea that the binomial is a discrete, the normal is a continuous, right? And so if we think about fundamentally what is the difference between discrete and continuous random variables, well, the difference is that with discrete, they're only going to be falling on the integer values in this case, whereas a continuous can take on any value along our number line, right? And so we can ask ourselves, for instance, if we think about our number line being here, right? And so we're just thinking about sort of, maybe 0, 1, 2, 3, and so on, right? If you're dealing with x is only going to be following the values up here, right? But if we're dealing with w, right, what do we do if we observe w in this interval here? Okay. And the answer is that we want to round w to the corresponding value of x, right? And so like that's what we would be doing normally is we'd say, well, we know that x can't be anything other than an integer, so just round it to the nearest integer, right? And so then the idea is that if that's between, say, 0.5 and 1.5, then we'd round this down. And if we observed something, say, up here, right, then we're going to round it up, right? And so what we need to do is we need to be able to apply what we'll call the continuity correction. And so the continuity correction is the process through which we change probabilities in approximations to account for w being continuous. Okay. And so the idea is that we're not actually going to take x less than or equal to x being approximated by this, right? We'll need to apply a continuity correction to fix this, right? And so how are we going to fix this? Well, I actually think it's easiest for us to think about this with some specific examples. And so why don't we look at these specific examples here? And the idea with these examples is that we're going to be thinking about, okay, if we have the corresponding event for x, what is the event for w that we're going to be thinking about, right? So for each of the following events, which is related to x being a binomial NP, specify the corresponding event related to w, which is our normal that's going to be used to approximate it. And so if we want to say, okay, x is less than or equal to 2, right? What event for w are we going to be using it? And so we have to ask ourselves, what values of w round to less than or equal to 2, okay? And so the point is that anything that's already less than 2, that's perfectly fine, right? But if we go up to as high as 2.5, right? So if we say w less than or equal to 2.5, this is always going to round down to being less than or equal to 2, right? Because if I gave you, say, 2.4, 2.4 rounds down to 2, right? And so if we know w is less than or equal to 2.5, this is going to correspond to x being less than or equal to 2. And so what we can say is the probability that x is less than or equal to 2 is going to be approximately the same thing as the probability that w is less than or equal to 2.5, because it rounds down to 2.5. Okay, let's try another one. X greater than or equal to 5. We're asking ourselves what values for w are going to round so that they would be greater than or equal to 5 if we're only considering the nearest integers. And here, if you take w to be anything which is greater than or equal to 4.5, right, this is going to work for us, right? Because anything that's above 4.5, so if you take 4.6 or 4.8 or 4.999, right, that's going to be greater than or equal to 5 once we round. And so then we can say, well, the probability that x is greater than or equal to 5 is going to be approximately the same thing as the probability that w is greater than or equal to 4.5. And note that these two cases are going to basically cover everything. We need to be a little bit careful, okay? But if you want x less than or equal to some value, then you want to increase w by 0.5. If you want x greater than or equal to some value, then you're going to want to decrease w by 0.5, okay? And we can always get to that by asking what values are going to round to the correct value. Now, the hard part comes if we have something like x less than 12. So my advice for something like this is always transform this to having the equality sign around. Okay, so we can write this as x less than or equal to 11, right? Because if x is less than 12, the highest that x can be is 11. We know it's an integer, right? And so if it's less than 12, then it has to mean it's greater than or less than or equal to 11. Apologies. And once we're saying, well, x less than or equal to 11, right, we're in the same as we were with case A. So what values for w are going to correspond to values which are less than or equal to 11? Well, w has to be less than or equal to 11.5.
So if we consider example D here, x greater than 14, again, this is one of those ones that we want to be careful about to make sure that we're doing correctly. And so x greater than 14, well, what's the smallest possible integer that's going to be greater than 14? We can write this as being the exact same thing as saying x greater than or equal to 14. And then once we're saying it's greater than or equal to 14, this is the same process that we can look at as going with w being greater than or equal to 13.5. Okay. And so the last example we have here is sort of just a compound event of sorts, right? And so if you're thinking about this sort of as two separate events here, right? We have 2 less than x, which we can write as 2 is less than x, right? And so if x has to be greater than 2, then x has to be greater than or equal to 3, right? So 3 is less than or equal to x, and we have x is less than or equal to 4, right? And so 3 less than or equal to x becomes 2.5 less than or equal to w, and x less than or equal to 4, right? Which values are going to round to this? Well, that's going to be x less than or equal to 4.5, and so then in total we can say 2.5 less than or equal to w less than or equal to 4.5, right? And so it's this process always of converting things into these less than or equal to event types, and then making sure that we're asking ourselves, well, what values are going to be the correct rounding values when we need to round our values here, okay? And so that's the general procedure, right? But then we can ask ourselves sort of how do we go about using this? And so we have this example here, and that's if we suppose that x follows a binomial 200.5, right? Then in terms of phi, what's the approximate probability that x is greater than 115? Right, so the first thing we want to do is figure out what is the normal distribution we're dealing with, right? And so what we know is that the expected value of x is going to be n times p, right? And in this case, n is going to be 200, and p is 0.5, right? And so the expected value of x is 100. Similarly, the variance of x is going to be n times p times 1 minus p, which is going to be 200 times 0.5 times 1 minus 0.5, which is, of course, 0.5 itself, right? And this is going to be 50. And so then we can take w to be a normal 150, okay? Then the second thing we have to do is do the event conversion that we were thinking about before, right? And so if we want x greater than 115, right, this is going to be the same thing as saying x has to be greater than or equal to 116, and so this is going to be the same as w greater than or equal to 115.5. Okay? And so now what we want to do is we want to say, well, what we know is that the probability that x is greater than 115 is going to be approximately the same thing as saying the probability that w is greater than or equal to 115.5. Right? And then we can use our negation tricks that we've seen before, right? So this is going to equal 1 minus the probability that w is less than or equal to 115.5. And now this is a normal probability that we've seen to calculate before, right? So we can use our standardization process, and we can write this as 1 minus phi of 115.5 minus the mean, which in our case is 100, divided by the square root of 50. Okay, and that's not going to be a whole lot easy to simplify, and so we can just leave it as that expression. Okay, and so that's really what there is to the normal approximation to the binomial, right? We want to figure out what's the normal that we're going to use. We want to figure out how do we apply the continuity correction, and then we'll actually do the approximation. Okay, and with that, that is
all of the content that we're going to cover for probability in this course this term. And so starting in the next lecture, so we won't get into this now, but we're going to start talking about what is probability versus statistics, and then how can we start thinking about statistics, right? So if we remember, well, with probability, we were assuming some model, right? So we have probability we assume a model, and then we ask, what are we likely to see? Okay. And so, we, for instance, assume that we know the probability mass function, and then we say, how likely is it that we observe x equals 5 if we have an experiment? With statistics, right, and we haven't started talking about statistics yet, but the idea is that we're going to do the reverse, right? So instead, we observe, and then we ask about the model. Okay, so what we do is we go out and we collect data, and then we say, based on what we've seen, what do we think is generating these data, right? And so one way we can sort of visualize this is we have some model, right? And with our model, we could think about this as being a probability distribution. We could think about this as being a probability function. We could think about this as being the expected value and the variance and whatever else, right? And then we have observations. And what we're sort of saying here is that with probability, we start at the model and we go to talking about our observations, right? So this is what we've been talking about with probability. How likely is it to observe a 3 if we know what the model is? With statistics, what we want to do is we're going to start from the observations and we want to talk about the model. And it's going to turn out that all of the tools that we've been discussing in probability up till now are going to be critically important for being able to do this, right? And so we're going to have to sort of build on all of this. Probability is going to become the language that we use to discuss statistics. However, this becomes a lot more applicable of a technique, especially if you're sort of in a science program, where you can think about going off and collecting data from an experiment and then using those data that you've collected to make conclusions about the real world. And so that's everything that I wanted to cover in today's lecture. And so starting in the next lecture, we're going to start discussing statistics, what statistics is, how we can start to do statistics.